I'll be explaining Chapter 11, Carboxylic acids and their derivatives, Part 2. I will not list the objectives, but I want to tell you that the main idea in this lesson, it's the esterification reaction, and all what comes here is something related to this reaction that we have to study in details. So this is why let's start by defining esterification reaction. As we said in the previous video, it is the reaction of ester formation starting from alcohol and carboxylic acid, or one of its derivatives. It means one of the carboxylic acid derivatives. Now you might not understand this, but in order to give a correct definition, I'm obliged, it means it is a must to add this, but for now you might not understand and I will ask you to forget about so far. So for you it's just the reaction between an alcohol and a carboxylic acid to give ester, as you can see here. The second idea that it has to be memorized by heart are the characteristics of esterification reaction. There are 3 characteristics and you will be asked about even in the exams, so you have to memorize them. The esterification reaction is reversible. It means incomplete one. This is the first. Second, it's slow. It takes many hours to be done. And it is athermic. Athermic, it means it is neither endothermic nor exothermic. So there is no exchange of heat with the external medium. So as I repeat, those 3 characteristics by heart and you will be asked about. What about the esterification equation? Pay attention here. Here is my carboxylic acid and here is the alcohol. Focus now on the colors used. Here is the hydrogen of alcohol and here the OH of carboxylic acid, as you can see. What will happen here? This red OH and this H here represented by red combine together in order to give water as a product. Now what will happen here? I will still have RO from alcohol and this part from carboxylic acid. What will happen? This oxygen here will come to this carbon and the ester will be formed having COO as functional group. And pay attention here, there is a mistake. It's reversible, so here there must have an arrow in the reverse direction. Let's consider this example. Here it's an esterification reaction between ethanoic acid and ethanol. As I said, the OH from the acid and H from alcohol will produce water, but while this part of the acid will combine with this oxygen coming from alcohol that is here producing this ester. To be noticed that the direct reaction or direct reaction is called esterification. It means in direction 1 here it is called esterification, and the reverse one here it is called hydrolysis, because we are decomposing this molecule. We will explain hydrolysis later. What about the IUPAC naming of esters? Here you have to pay attention because esters have special rules for naming. First of all, we have to divide the ester chain into 2 parts. The part coming from alcohol and the part coming from carboxylic acid. Now the question is how to identify the part coming from alcohol. It is the part that is directly bonded to the oxygen that is alone, to the oxygen in that chain. While the carboxylic acid or derivative, as I said, I'm obliged to repeat it, but you have to forget about so far. The carboxylic acid part, it is the part that originated from carboxylic acid or one of its derivative. Now what is the rule? The rule is to consider the part coming from alcohol as an alkali group, it means as a branch, and the part coming from the carboxylic acid will end with the suffix 8. If you can't understand how to name an ester, that's normal. Let's go to an example to understand how we have to proceed. As I said, the name of an ester contains the names of the alkali group from the alcohol and the carbon chain from the acid with 8 ending. Look at this example. Here is the ester C, double bond O, and oxygen. How to know the part coming from the acid? We will look at this carbon with the double covalent bond O and the R that is beside. So this will be directly the part coming from the carboxylic acid. While where is this oxygen with single covalent bond and the R coming after it, this will be the part coming from alcohol. So the alcohol here, what do I have to add here to obtain the original alcohol? I have to add H. So the alcohol from which this ester derived is methanol, and the carboxylic acid here from which derived this part, I have to add OH here to obtain the original carboxylic acid. It is with 2 carbon atoms, it is ethanoic. So what will be the name? We said that the alcohol part, it's considered as an alkali group without considering the presence of oxygen here. So it will be with 1 carbon atom, it is methyl because the alcohol is methanol. And here it was ethanoic acid, so it turns to be ethanoate. So the name that consists of 2 words, it is methyl ethanoate. Let's practice here in order to know. I will give you those. Look. Here is the part coming from the alcohol. How did I know it? Because here the single oxygen alone that is not connected by double covalent bond to this carbon, and the R that is next to it, this is the part coming from alcohol with a 3 carbon, so it's a propyl because it is considered as alkyl. And here is the part coming from the acid with 2 carbon atom, it is ethanoate as we said. Look at this example. The part coming from alcohol have 5 carbons, so it would be called pentyl. And the part coming from the carboxylic acid, it is ethanoate. A third example, it's octyl with 8 carbon atoms, and here is ethanoate. And the last example, 2 carbons from the alcohol, so it is ethyl, and 4 carbons for the carboxylic acid, it would be butanoate. Now, what if the ester is branched? Here also there is something specific for ester. This is why let's consider this example. Here is the ester with COO. Let's cut this ester into parts. This is the part coming from the acid because C double covalent bond, and this is the part coming from alcohol. Now how to give numbers? Here you have to name it in that way. This is carbon number 1 because in the alcohol this carbon was number 1 was when here we had H. So we will start naming in this direction for alcohol and in that direction of carboxylic acid. So here carbon 1, here is carbon 2, and here is carbon 3. For the acid part, here is carbon 1, 2, 3, and 4. Now the branch in the alcohol part is methyl connected to carbon number 1. And the branch in the acid part is also methyl connected to carbon number 3. What would be the name? Don't forget that the alcohol part it's considered as alkyl. 1, 2, 3, it would be propyl, but we have a branch, so it will become 1 methyl propyl, 1 methyl propyl, and the 3 methyl butanoate. And this is in an example, a typical one that you have to memorize by heart in order to give names for all esters you might face. Let's do an application. So write the equation of esterification reaction between 1-propanol with ethanoic acid. Do a pause, worked on a scratch paper, and then here is the solution. Another application, you have to write the equation of the reaction between 3-methylbutanoic acid and 2-butanol. Also, you have to give the name of the ester formed. Here also, do a pause and do it alone. Here is the solution. Don't forget that esterification is a reversible equation. Now, what about the yield of esterification reaction? Yield is not something specific for esterification, but for esterification there is something different from other examples. Yield in general, not only for esterification, is the ratio of the experimental mass or the real mass, the actual mass obtained experimentally, or number of mole. It can be calculated either regarding mass or number of mole of the ester produced to its theoretical mass or expected mass or number of mole. You know well that this is the formula of the yield. I repeat, it is the actual or experimental number of mole or mass of a product. Here we choose to be the ester because the reaction is esterification, over the theoretical number of mole of ester or the mass of ester multiplied by 100. So let's do this application to understand how to deal with the yield of esterification. In an experimental setup, we put this volume of methanol that is mixed with 30 grams of ethanoic acid and boiled in reflux heating. Now this is also a new term, very important, that will be explained after a while, until equilibrium is established. The resultant mixture was titrated by sodium hydroxide, and the number of moles of ethanoic acid remaining was found to be 0.17 mole. This is the given. What is the first part? It's to write the equation of the reaction taking place. Please do a pause. Pay attention that the alcohol is methanol and the alcohol is ethanoic acid, and write the equation. And here is the solution. Number 2 now. As you can see here, I copied the given here as is, and I copied also the equation written in part 1 because we might use it here. In part 2, they are asking us to show that the reaction mixture is equimolar. What is equimolar? Equimolar, it means equal number of mole for reactants. I repeat, the reaction mixture is equimolar. It means the reactants will have equal number of moles. Let's work first of all to calculate the initial number of mole in order to see. The reactants are the acid and the alcohol. So what is N0 of alcohol? It is simply the mass of alcohol over the molar mass. But we don't have the mass, we have rather the density and the volume of alcohol. So the mass of alcohol will be density times the volume over the molar mass. As you can see, the molar mass is given here 32. The density is given in gram milliliter minus 1. We don't have to convert it. Why? Because the volume here is given also in milliliters, so it's enough to multiply it in order to obtain the mass in gram. So the initial number of mole of alcohol is 0.5. What about that of acid? Let's calculate it. N of acid initial is equal mass of acid that is given here, 30 gram, over molar mass of acid that is given here. So the answer is 0.5. As you can see, the initial number of mole of both is equal. Therefore, the mixture is equimolar. I repeat, equal number of initial moles. Again, I copied here the given. Determine the percentage yield. Here we have to apply the formula. But we don't have to forget that the esterification is not a complete reaction. But in the calculation of yield, we have to suppose that the reaction is complete, and we have to work in a stoichiometric way as if it is a complete reaction. I repeat, we have to suppose that the reaction is complete. Why? In reality, the reaction is not complete, and this is a specific calculation and a specific supposition for the determination of the percentage yield in case of esterification. So, according to stoichiometry, to the stoichiometry of the reaction, N initial of the acid here is equal to the N theoretically formed of ester, because the theoretical, it means according to the stoichiometry, it means got by calculation and not in reality in the experiment itself. So N of the ester theoretical, it is 0.5 mole. Perfect. Now how to find N experimental of ester? Referring to the given, we have nothing related to ester that is formed. But what do we have? Look at this sentence. The resultant mixture, it means the product and the reactant mixed together, because don't forget that this is a reversible reaction, so we still have part of the reactant and part of the product that is formed. The resultant mixture at equilibrium, it means, was titrated by sodium hydroxide. And I don't care now about the details of the titration. I'm caring about the number of moles of ethanoic acid remaining was 0.17 mole. So pay attention. I have the initial number of the acid and the remaining number. So what about the reactant amount of acid? It is here. N reacted simply equal to n initial, that is 0.5, sorry, minus n remaining. It will be equal the following, 0.033. Now, you have to pay attention that n reacted of the acid, according to the stoichiometry, it is equal to the number of mole of ester formed, and this will be the experimental value of ester formed, because in reality, we found that we have 0.17 mole of acid that remains, and this number of mole that reacts. So, the yield, it's the actual or experimental number of mole of ester over the theoretical number. It is equal to 0.33, the theoretical, I repeat, over that. This is the experimental over theoretical. Pay attention that always for all kinds of chemical reaction, not only for esterification, the yield is less than 100%, because always we have experimental errors and loss. This is why the experimental yield or the yield will be less than 100. It means the theoretical or the experimental is less than the theoretical. Now, equimolar and non-equimolar mixtures, we've already explained it, but let's repeat it. Equimolar mixture is the number, or if the number of mole of the carboxylic acid and the alcohol introduced into the reaction mixture is equal. Simply, in that case, the mixture is said to be equimolar. While in the other way around, if the number of the alcohol and carboxylic acid is not equal, the mixture is said to be non-equimolar. Here it's a remark that the yield of esterification reaction at equilibrium in equimolar mixture is usually less than the yield of esterification in case of non-equimolar. Actually, I cannot explain it, and I doubt to be asked about this here, but it just is a remark to be given. Effect of the class of alcohol on the yield. Here, those values here are found experimentally. I cannot explain it in this class. So, if an equimolar, I repeat, an equimolar, and it is written in red, reaction mixture is at equilibrium, also in red, the percentage yield of a primary alcohol, if the alcohol used is primary, is 67. And this value is constant for all kinds of primary alcohols. And for secondary alcohols is 60%. Also, this is a value that is constant. And it's 1 to 5% if the alcohol used is tertiary. So what do we have to memorize as a conclusion? If we have equimolar mixture of alcohol and carboxylic acid, when reaching equilibrium, and if the alcohol is primary, then the yield is around 67% by heart. It is found also that if the mixture is equimolar, we are at equilibrium, we have secondary alcohol, then the percentage yield is 60%. Again, equimolar, equilibrium, tertiary alcohol, the yield is 1 to 5%. So the least is for tertiary alcohol. Now, let's consider this special case. If in an exercise we ask you the following: if the esterification reaction of a primary alcohol has a yield 60%, pay attention, it's a primary alcohol, so we are waiting for a yield to be equal to 67. So why it's 60? How can you explain this result? Simply, here, they didn't say that we reached equilibrium, so we still need a little time in order to reach equilibrium. So the reactant will react a little bit more in order to produce more product. So the yield is 60% less than 67. This can be explained by the fact that the esterification reaction didn't or doesn't reach equilibrium yet. Another special case, also it can be asked in an exercise, if the yield of esterification of an alcohol is equimolar mixture of unknown class, so I don't know the class of alcohol, if the yield is 60%, here pay attention, 60%, I have memorized it. It's the percentage of what? Of a secondary alcohol. But here it's of unknown class. But what did they say before reaching equilibrium? What is the class of the alcohol used? If it is at equilibrium, it would be directly secondary alcohol. But before reaching equilibrium, it means we still have time to reach equilibrium and to obtain more product. So the yield will be increased, and this is the answer. So the alcohol actually is primary, since the yield of the reaction of an equimolar mixture of a primary alcohol at equilibrium is 67%. That is greater than 60%, which is not at equilibrium. Thus, with extended heating, the yield will become 67. Okay? Finally, let's talk about heating reflux. As you can see, here is heating reflux. I have the alcohol and the carboxylic acid put here, and we are heating. This is a heating apparatus. So the vapor will go up through this condenser that is vertical. Here the water coming in and out will cool the vapor. So as you can see, the vapor will condense back and return again. Here, as I said, it's a reversible reaction. So the components here are the alcohol, the acid, the ester, and water. All of them will evaporate and will condense back. So this is the importance of heating reflux. Reflux involves heating the chemical reaction for a specific amount of time, done by connecting a vertical condenser to a flask containing the reaction mixture and something called boiling chips I want to explain after a while. Here is the real drawing. What is the importance of reflux heating for a longer period of time? Avoid, this is by heart, avoid the loss of components of the reaction. When the reactants or the products together evaporate, don't forget they exist at time because we are in a reversible reaction where reactants and the products are still present together. So when the reactants or the products evaporate, they meet a cold surface here in the condenser. Then it condenses back to the reaction system, and this is why we avoid any loss. The third thing, we are heating, and don't forget that temperature is a kinetic factor. So heating reflux increases the rate of the reaction because, as we said, esterification is a very slow reaction. It takes tens of hours in order to end. Now I will ask you here to draw this and to memorize this by heart. As you can see, look here at number 2, boiling chips. What are the boiling chips? It's simply small specific stones added to the reaction mixture here. Why? Here simply because they will mix the mixture continuously. Prevent bumping, it means, and ensure even boiling. Ensure even boiling, it means the heat will be distributed evenly all around this flask, so it will not be broken, and pressure will not increase highly here for this one to be increased. So this is the role of the boiling chips. Okay, you have to memorize it also. Role of the vertical condenser, as I said, is to condense the components. Pay attention, I said components, it means reaction and product at time in case of esterification because it's a reversible reaction of the reaction back to the mixture and avoid their loss. This is all about esterification. Thanks for watching and see you